In a previous video, we explored random walks in Python and discussed the idea that share prices could be modeled using random walks. Hence, we wrote the current share price PT as follows. PT is equal to the previous share price, PT minus 1, plus an error term, which we called a white noise process, epsilon t. The previous share price, PT minus 1, is the best prediction for the future, as the so-called white noise process cannot be predicted. We simulated this equation, but you might wonder whether this model is satisfactory for share prices. Depending on the initial share price P0, this model might be acceptable for short periods. Over longer periods, however, we run into the problem that the process does not have any bounds. Hence, it is possible that the simulated share price becomes negative. Now, this is not very meaningful. Another issue is that our current model does not permit a long-term trend, a so-called drift component. Let's have a look at some real data. I downloaded the share price of Tesco from Yahoo Finance. And you navigate to historical data. You can adjust the time period. We just take all the stuff they have and then download our data. The data comes in a CSV format, which can be easily imported into pandas. I have done another video on how to download financial data from Yahoo Finance using an API in Python. Now, this is very useful if you have several time series to download. I saved the CSV file in the same folder where I keep my Python script. Hence, I do not have to change the directory to load the data into pandas. Let's start our empirical investigation. We start by importing several libraries which we will use for this particular problem. Then I import the data from our CSV file. I name the file and I use the read_CSV function in pandas. This provides a pandas data frame. Now, looking at this data frame, our index is simply counting our observation in the Python fashion starting at 0. In my case, it would be useful to have a time dimension starting at 1. So what I do is I take this index, I add 1 to it, and I call this my time. I will use it later to estimate the drift component, which is equal to a linear time trend. If you're new to pandas, watch my other video which provides an introduction. So this line of code will provide my time dimension using the index and adding 1 to it. Now we set the index based on our date variable. Please note that you have to reassign the data frame. This method does not change the original data frame. Finally, we plot using the plot method in pandas. We refer to daily closing prices using the attribute close. So this shows our share price from 1988 to the current period. Next, we try to estimate the long-term trend. Basically, we add a drift component denoted mu to our equation as follows. This suggests that the share price increases by a fixed amount in pound terms at each time step. Is this really plausible? Well, if the current share price is, say, £100 or £10, a fixed increase in value is quite different in percentage terms. Well, let's run the model and see what our data would suggest. So we run a linear regression to obtain the drift, which refers to a linear time trend. That means that after each time step, the share price increases by the drift component. We fit the data in line 30. We show the results in line 33. and the model parameters. So this gives you a list of coefficients. So this is our regression output. Looking at the adjusted R-squared, we obtain around 31.4, and you can see that the coefficient, so this is my drift component, is significantly different from 0 looking at the p-value. So there is a positive drift. Then down here you see the intercept and the coefficient for time. So these are my model parameters or coefficients. We can add the prediction to the data frame. Here we use indexation, 0 for the intercept and 1 for the drift component to compose our linear prediction. An alternative approach is to use the predict method on the results object, but one needs to be careful with the dimensions of the array when merging it with the data frame. Finally, we plot the share price and trend. Well, this does not look too impressive. Now, what should we consider next? We have the problem of potentially negative share prices, and looking at the drift, it doesn't seem to be very plausible to assume a constant change in pound value over time. So what to do? Well, let's look at the literature. The literature suggests to modify our model using log share prices. This approach appeared in a paper by Osborne in 1959, and it was later discussed by Fama in 1965. I provide links to both papers in the description. It's interesting to note that Osborne's work belongs to the econophysics literature. There's a lot of overlap and cross-fertilization going on between physics and finance in this period. Let's look more carefully at log prices. So here we take the log on both sides. We obtain the ln of the current share price, the natural logarithm, as the ln of the previous share price, plus again a white noise process denoted epsilon t. So taking now an e function, so exp on both sides yields the following. We obtain the share price, and here exp ln pt minus 1 plus epsilon t. And now you might remember the rule that e to the power of a plus b is equal to e to the power of a times e to the power of b. We now use that to simplify as follows. Pt is equal to pt minus 1 times e to the power of epsilon t. P1 is equal to P0, the initial value, e epsilon 1. We can continue to the next period. P2 is equal to, well, P1 e to the power of epsilon 2, or using our previous finding, P0 e to the power of epsilon 1 plus epsilon 2. Now we can continue this little game up to period, say, capital T, and we have the initial value of the share price times the e function, and here we have the sum of all these white noise processes, or to be precise, the realizations of the white noise process starting from 1 going up to capital T. This model is also called Geometric Brownian Motion, but one needs to be a bit careful as Brownian motion refers to continuous time. It is obvious from this equation that Pt is strictly positive, well, as long as the initial price is strictly positive, which is a given. By focusing on log prices, we address the issue that random walks could become negative at one point. Now we add a drift component mu to the equation. We assume that share prices increase by a fixed percentage point over the long run. This might be more plausible than a constant amount in pounds term. Let's try this in Python. We take log prices and add them to our data frame in line 44. Then we rerun our regression model, fit our data and add our linear prediction. Now looking at the adjusted R squared, it's now 0.463 compared to 0.314, so quite a substantial improvement. If you're new to regression analysis, have a look at this video. Then we add the prediction as before using the intercept plus our slope coefficient, so this is our drift times time. And finally, we visualize. Now compared to our initial modeling attempt, the log model looks an awful lot better. Of course, in particular, if you're a chartist, you might now start trying to fit some trend lines. But I leave it to another video to discuss whether this is a plausible way of analyzing share prices. Now let's simulate share prices using the code we developed in the video on random walks. Of course, now we modify the code taking our logs into account. So let me just grab the code, copy paste that, and I move everything now into a function except the plotting because that's later visualization. I call this share sim for share simulation, and all these parameters I could move them basically up here, and I will modify them slightly because now we are in a log model, so these changes might be too strong for the log model. So here the initial value I reduce it a bit because we are now in the log, otherwise it becomes quite large, and the time step, let's make it a bit smaller, and we make a smaller step change as well, so that should smooth it out a little bit. Let's tidy this up. The white noise process remains as before, so this setup is also fine. The only line here is line 78 because here we need the log price, so we know that the price is driven by the previous price times VLN, so NP EXP of my error component. So I have to put this into brackets, and then I have to call the function, which I do here. So I assign it and I just call it. I use here the default settings, which I specified here with the equal sign. So I can just call that, and that should simulate my random walk based on the log model. Let's give that a try. Haha, what did we forget? The column. Good, let's try it again, and here we are. We now have our share price simulated. Good, I see you next time.